Okay, so this gives rise to something that's going to be really important for us to understand as we go forward, which is something called the material derivative. So we've just talked about the difference between an Eulerian reference frame and a Lagrangian reference frame, and we're going to need a way of converting between one reference frame and another. Visually, a very good way of seeing this will be to watch the video called Eulerian and Lagrangian descriptions, where you'll see visually very good ideas of this. In particular, you'll see the idea of using small material elements that may be labeled as a continuous piece of medium that's flowing into a contraction or into a region at a velocity v. And you'll see that as they flow in, that they get deformed, and so the material changes its shape, and as it changes its position, it also changes its speed. And so the velocity here, v2, will be bigger than the velocity v1. You'll also see that if you look at components or material elements that are off the center line, that as they flow in, they also get faster, but they also will get deformed. And we'll also see that deformation is important. We're not going to think about deformation in this moment. We're just going to think about accelerations and translations of position. So we'll come back and we'll think about deformation. But for now, let's just think about a material element that's moving along the symmetry line along the middle of this. So in the Lagrangian reference frame, if we're interested in, say, the rate of change of a variable, that variable could be a vector quantity such as the velocity, but it could be something else as well. Then if we're associating that with a particular particle, as we do in the Lagrangian reference frame, then we're really just interested simply in a statement of what would be the time rate of change of that quantity. In a Lagrangian description, then that's the position of the particle, which we know gets specified in terms of where it was initially and the time that's elapsed since that original value. And so we could also write this equivalently as a partial derivative. It's the rate of change of f with respect to time, where f is a function of position and time. And the quantity, when we write a partial derivative, we really mean something is being held constant. And what's really being held constant here is the identity of the particle. So we're really thinking about following a material of constant identity. So that might be, for example, this particle as it moves into the contraction plane. So that's easy, but in the Eulerian description, then we don't really follow a material point directly. Instead, we're really thinking about partial derivatives are expressed in terms of position in space and time. By which I mean that typically in an Eulerian description, I might have a sensor that I could put into the flow at position 1, and another sensor that I could put into the flow at position 2, and I could plot what the velocities look like as a function of time, as maybe I turned a valve up and down here. And so I would find that velocity 1, v1, is lower than v2. And if we just observed it and it was steady flow, then this would look like there is no change in time. And if I now turned a valve up and I accelerated the flow or I increased the speed, I might find that the velocity here increased. But then I'd find that the velocity here increased even more as well. And so if I opened a valve here, So there's two quantities that we can measure. One is variations in time, and one is associated with variations in position. And somehow we need to connect that Eulerian description with the idea that in a Lagrangian description, what I would experience is that I'd be moving along here, and then I would accelerate as I move in here, even if the flow is steady, because I find myself going at a faster velocity here than I was here. And so we need a way of converting between one and the other. So how do we convert between this? So to convert, between these two descriptions, which are completely equivalent, and the way we're going to do that conversion is going to be in terms of something called the material derivative. And because this operator shows up so much, we're going to give it a special notation. And it is a differential operator, and it's a time rate of change of something, so we'll indicate it as a rate of change with respect to time, and we're going to give it this symbol big D by dt. And so what we'll want to do is we'll want to think about how to understand this, and this reference frame is maybe a good way of thinking about it. So all I have to really do is, if I want to think about some quantity, some arbitrary quantity f, I have to recognize that f can change for two different reasons. It can change maybe even if I stay at a fixed point in space, because I change the velocity. So I should write it as having variations with respect to time. And just to be careful, we'll remind ourselves that when we write a partial derivative, we should really specify what would be constant. And so here, in an Eulerian reference frame, what is constant is the position in space. We could measure this quantity here, or we could measure this quantity here. But then I also have to recognize that I can change associated with changes in position. And position is a vector quantity. Time is a scalar, of course, so I should really write this in terms of different values, xi, summed up over all of the different changes here, where I would be equal to 1, 2, 3 for changes in x, y, and z. And I might write this with a summation right here. And again, when I write a partial derivative, to be careful, we should really write what is being held constant, which is time. Now, people in fluid mechanics will frequently stop writing this quantity and stop writing this quantity, and then we'll also use the Einstein summation convention that says if we're summing over this, if I see a repeated index, I don't have to write this. So frequently you'll see this written without all of these careful quantities. And now if we want to calculate a derivative, we'll take this and we just want to divide it by time. So we're just going to divide by time. And so we'll end up with a quantity that looks like df by dt. Again, reminding ourselves that this should really be written, to be careful, with a constant position. And then here, if I divide by d time here, then I'm going to get, this will cancel, but here I'm going to get dx over time, which is just the rate of change of position with respect to time. And so at a particular instant in time, that is nothing but the velocity at that point. So we can certainly write this in terms of velocity, and we can write it as a summation that looks like this. And again, there's a summation right here over the different values I. And because this is a combination of a vector quantity, which is the velocity, and another vector quantity, which is the position, both of those are vectors, then we'll write this in a simpler way as df by dt, which is the time rate of change, plus the velocity, which is a vector quantity v, and then the gradient operator, or grad, or nabla, of the quantity f. And that quantity is our material derivative, df by dt. And so this is an important result that we'll use continuously throughout this class. And you can see that it is indeed an operator on a quantity f that would go in here. And that quantity f might be a scalar. It could be the temperature, but it can also be a vector. And as I draw on here, it's a vector. So this could be a scalar, or it can be a vector. If it's a vector, then we have to be very careful about this operator, and we'll think more about that in a moment, because a common one that we'll be very interested in will be the acceleration. So the acceleration is something that if we were to think about it as a second derivative of position in a Lagrangian sense, it would be the second derivative of the position of our particle with respect to time. That would be the acceleration. In the Lagrangian world, it will be the material derivative of the velocity field, which would be dv by dt. Maybe here we'll just remind ourselves that that would be at a constant point in space plus the velocity dotted into the gradient of the velocity. And that's expressed at a constant instant in time. So as you watch this video, you can see that a material element can accelerate because of time rate of changes at a fixed position, as we would see along either one of these at a fixed position. So this would be at a position x2. This would be at a position x1. But also I can accelerate even if the flow is steady, as a material element goes from here and as it flows into the contraction and it ends up at a new thing here, then this term will give rise to an acceleration just because of changes in position. So it's nothing to do with time changes, it's to do with position changes. And because of that, people will often give this a particular name. They'll call this the advective term. So you'll see people refer to an advective term. In the particular case, if this was a temperature, then sometimes you'll also see people will call this convective in the case of temperature. And so when people are talking about convective terms or advective terms, this is the term that they're interested in. And the thing to recognize is that this is a very nonlinear term.